Before we look at this problem, we're going to review some algebraic formulas. First of all, if we have 7 to the n plus 1th power, we can break down as 7 to the nth times 7 to the 1st. Because when we multiply exponents, if they have the same base 7, we keep the base 7 and add exponents. So 7 to the nth times 7 to the 1st equals 7 to the n plus 1th power. And 7 to the 1st, it just means 7. So if we have this first power, the 1 can be omitted. And we can also, the next step we can do is we can break down 7 as 6 plus 1. Because 7 equals 6 plus 1. And the reason we do that is we can distribute, because this is multiplication here and the plus here, we can distribute 7 to the nth to each one in the parentheses, each term. So we have 7 to the nth times 6 plus 7 to the nth times 1. Okay, so this part will be used in our proof. Now, let's look at how we use mathematical induction to prove this statement that 7 to the nth minus 1 is divisible by 6. So when this is a number here, after we pick a number, integer n, and plug in here, we will get a number. For example, when n equals 0, let's try to do the first step, the basis step. So if n equals 0, 7 to the nth minus 1, we replace n with 0, so we get 7 to the 0 minus 1. And any number raised to 0 is equal to 1, and 1 minus 1 is equal to 0. So when n equals 0, 7n minus 1 is 0. So this part will become 0. So it's like saying prove that 0 is divisible by 6, which is obviously true because, so I would say since 0 equals 0 times 6 or 6 times 0, that tells us 6 goes into 0. 6 divides 0. Or you can say 0 is divisible by 6. 0 is divisible by 6. Now, well, similarly, if you want to prove this statement is true for n equal to 1, we replace n with 1. So if we replace n with 1, we get 7 minus 7 to the 1st, which is still 7, minus 1, we get 6. And 6 is divisible by 6. That is true. If n is 2, we get 7 squared. That's 49 minus 1, 48. 48 is divisible by 6. And similarly, we can, kind of pick a few numbers, integers for n to verify this is correct. But we cannot use that as a proof because we have to prove this for each integer. Every single integer, 0, 1, 2, 3, 4, 5, 6, 7, all the way to infinity. Well, so we cannot prove like the basis case and prove this statement is true for every single integer. So we have to have this inductive step. So in this inductive step, first we assume this statement is true. So we assume the statement is true. Statement is true for n equal to k. And our goal is to prove the statement is true for n equal to k plus 1. Now, so it's kind of like a condition, proving a conditional statement. If the statement is true for n equal to k, then the statement is true for n equal to k plus 1. So what is the statement if n equals k? So we have to write it out so we can prove it. The statement n equals k, so we replace n with k in the expression. So we get 7, it's like saying, so I probably should put or, 7 to the kth power minus 1 is divisible by 6. So this is the statement right here. This, let's see. So this whole thing is the statement. So when n equals k, we replace n with k, and we get this statement, 7 to the kth minus 1 is divisible by 6. And now, what is the statement if n equals k plus 1? So similarly, we replace n with the k plus 1. So the statement is going to be 7 to the k plus 1th power minus 1 is divisible by 6. So that's like proving if 7 to the kth minus 1 is divisible by 6, then 7 to the k plus 1th power minus 1 is divisible by 6. So we're using the first statement here, underlined in blue, to prove this statement here. Okay, so we have to use the definition. What do we mean by divisible? A number is divisible by 6. A number is divisible by 6 means, by definition of divisibility. So I'll just say by the definition of divisibility. Divisibility, 7 to the kth power minus 1. We can factor a 6 out of that number. It doesn't look like a number now because it looks like edge break expression, but we should know k is an integer. So if we plug an integer here, this will be a specific number. So if you want to prove 6 goes in there, we can factor out a 6 times some kind of integer. So let's not use n or k because they have already been used. So we can use m, and well, m is an integer. Okay, and similarly, if we want to prove 7 to the k plus 1 minus 1 is divisible by 6, and that means we have to prove 7 to the k plus 1 minus 1 we can factor a 6 out of there times an integer. So what's missing here is that integer. So now we have to use what we have. We know 7 to the k minus 1 is equal to 6 times the integer. How do we get an integer for here? Okay, so we're gonna have to make connections between the left-hand sides because they are different, left-hand sides. And so use what we have talked about at the beginning, this part, algebra part. We rewrite 7 to the k plus 1th power as this right here. Okay, so let's see. This is kind of going backwards, so I'm gonna start from this last one and go back and go back and then go back. I guess we can. Either way works. We can start with the bottom. Let's start with the bottom. This one here. So 7 to the k plus 1 minus 1. This expression, this number, I want to factor out a 6. But first of all, I have to rewrite this as 7 to the k times 7 minus 1. And then I break down 7 as 6 plus 1 minus 1. And then I distribute 7 to the k to both of them. So I get 7 to the k times 6 plus 7 to the k times 1. Times 1, I'm just going to omit it, minus 1. So what we actually did was, here, if you think about the meaning, that means we have 7 copies of, we multiply 7 copies of 7 to the k. And that means we can, it's like multiplying 6 copies of 7 to the k plus another copy of 7 to the k. Altogether, that would be 7 copies of 7 to the k. The reason we want to do that is because after I do that, I notice that 7 to the k minus 1, that's exactly the left-hand side of the given condition. And so I can, keep the first part right here, 7 to the k. We have 6 copies of 7 to the k. Plus, I'm going to replace 7 to the k minus 1 with 6m, because 7 to the k minus 1 equals 6m. And now notice that both of them contain a factor 6. So there's a 6 here, so we can factor out a 6, and we're left with 7 to the k plus m. And that is the integer we're looking for that's missing here. So what is, look at this long expression. We started with 7 to the k plus 1 minus 1. That's the left-hand side. We did all this algebraic work, and we get the final answer. We were able to factor out a 6 times 7 to the kth plus m. So we can say, if we can write a number or expression as 6 times an integer, we can specify here where 7 to the k plus m is an integer. So I can say 7 to the k plus 1 minus 1 is divisible by 6. Okay, so we summarize the proof of this mathematical induction. We always do basis case, starting with whatever they give the least integer of n. So in this case, n is equal to 0. And we replace n with that 0 and the least integer, and to prove that statement. Usually basis case, because after we plug into a number, we're just going to get a number, so we won't have variables. It's going to be easy to, so it's easy to prove 0 is divisible by 6. But the inductive step will involve variables, so we usually have to use a lot of algebra in this part, inductive step. So we always assume whatever the statement property they give us is true for n equal to k. So that means you have to replace the variable n with k, and then write down your goal, write down the statement for n equal to k plus 1, which means you have to replace n with k plus 1. So that's how we get these two statements here. So like this one and that one. So it's kind of like using the first one to prove the second one, and that part connecting, or the deductive part, usually you have to use a lot of algebra to try to make connections between the algebraic expressions.